So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're lying still. Maybe you're under a blanket, your head on a pillow, and everything feels perfectly motionless. But you're not still at all. The Earth is spinning, and at the equator that spin carries the surface along at about 1,000 miles per hour. On top of that, the whole planet is swinging around the sun at roughly 67,000 miles per hour. And the sun itself is drifting through the Milky Way at nearly 500,000 miles per hour. You're hurtling through space right now at an almost incomprehensible speed, and yet you feel absolutely nothing. No wind in your hair, no rumble beneath you, no sense of motion whatsoever. Just stillness. That little puzzle, why you can't feel how fast you're moving, is one of the oldest questions in physics, and it's the thread that eventually leads, through centuries of argument and genius and wrong turns and breathtaking insight, to the theories of relativity. That's what we're going to talk about tonight. Not in a rush, not like a textbook. Just the story of how human beings slowly, painstakingly figured out what motion really means, what space really is, what time actually does when you're not looking at a clock. It's one of the most extraordinary intellectual adventures in history, and it starts a very, very long time before Einstein. Let's go back, way back. Ancient Greece, around the 4th century BC. A man named Aristotle is thinking about the world, and he has some ideas about motion that will dominate Western thought for nearly 2,000 years. Aristotle looks around and sees that things on Earth behave in a pretty straightforward way. Heavy things fall. Light things rise. Everything seems to have a natural place it wants to be. Rocks want to be on the ground. Fire wants to go up. And if you want to move something sideways, push a cart, throw a javelin, you need to keep applying a force. The moment you stop pushing, the thing stops moving. That's how it looks anyway. Aristotle concludes that the natural state of earthly objects is rest. Motion requires a cause, a mover, something actively pushing or pulling. Take away the cause and motion ceases. Now, there are problems with this. Even in Aristotle's time, people noticed that when you throw a ball, it keeps going after it leaves your hand. Nobody's pushing it anymore, so why doesn't it just drop straight down? Aristotle's answer was a bit of a hand wave. He suggested that the air rushing around the object somehow keeps pushing it forward. It's not a great explanation, and some of his contemporaries weren't entirely convinced. But Aristotle was Aristotle. His authority was enormous. And his framework, that rest is natural and motion needs a cause, became the default assumption for philosophy and early science across the Mediterranean, the Islamic world, and eventually medieval Europe. Here's why this matters for our story. If you believe that the natural state of things is to be still, then you have a problem with the Earth. Because if the Earth is moving, spinning, orbiting, then why don't we feel it? Why doesn't everything fly off? Why does a ball dropped from a tower land at the base of the tower instead of being left behind as the Earth whips away beneath it? These are genuinely good questions, and for a long time, the simplest answer seemed to be that the Earth doesn't move. The Earth sits at the center of the universe, perfectly still, and everything else, the sun, the moon, the stars, the planets, revolves around it. That's the geocentric model, and it was codified beautifully by a Greek-Egyptian astronomer named Claudius Ptolemy around 150 AD. Ptolemy built an elaborate mathematical system of circles upon circles, epicycles they're called, to explain the wandering paths of the planets across the sky. And it worked. Not perfectly, but well enough to predict eclipses and planetary positions for centuries. The Earth was the fixed, unmoving center of everything. And honestly, that feels right, doesn't it? Step outside on a clear night and watch the stars wheel overhead. It really does look like the sky is rotating around you. Your senses tell you that you're standing still, and the universe is moving, trusting that intuition isn't foolish. It's human. And it held for a long, long time. But let's jump forward now to the 1500s, to a quiet, cautious church, official in what is now Poland. Nicholas Copernicus, he's a canon at a cathedral, a man with duties in church administration and medicine, but his real passion is astronomy. And he's been bothered for years by the ugliness of Ptolemy's system. All those epicycles, all those patches and adjustments needed to make the math work. Copernicus has an idea that simplifies things dramatically. What if the Earth isn't at the center? What if the Sun is at the center, and the Earth is just another planet orbiting around it? Now, Copernicus isn't the first person to suggest this. Aristarchus of Samos proposed a sun-centered model way back in the 3rd century BC, but it didn't catch on. Copernicus, though, does the math. He works out a detailed system where the planets, including Earth, orbit the sun in circles. And while his model still needs some epicycles of its own, because he insists on perfect circles, and planetary orbits aren't actually circular, it's cleaner, more elegant. It explains naturally why the planets sometimes seem to move backward in the sky, a phenomenon called retrograde motion that had always been awkward for Ptolemy's system. In the Copernican model, retrograde motion is just what happens when the Earth overtakes a slower outer planet in its orbit, like passing a car on the highway and watching it appear to drift backward against the distant scenery. Copernicus is so nervous about the controversy his idea might cause that he delays publishing his major work, De Revolutionibus, until 1543, the year he dies. Legend has it that a copy of the printed book was placed in his hands on his deathbed, though whether he was conscious enough to appreciate it is debatable. But here's the thing. The book doesn't immediately set the world on fire. It circulates among astronomers, some of whom find the math useful, even if they don't believe the Earth actually moves. The Catholic Church doesn't ban it right away. It's a slow burn. But the fuse is lit. Because now, people have to seriously grapple with a question that cuts right to the heart of what motion means. If the Earth is moving, why can't we tell? Think about what that question really asks. If you're on a ship sailing smoothly across a calm sea and you're below deck with no windows, can you tell the ship is moving? You drop a ball, and it falls straight down to the floor, just like it would on land. You pour a glass of water, and it pours normally. Nothing inside the cabin betrays the motion. This is something sailors had known for centuries, and it's the key insight that starts to crack open the old Aristotelian framework. The person who really grabs hold of this idea and wrestles it into something revolutionary is Galileo Galilei, born in Pisa in 1564. Galileo is one of those figures who's so famous that it's easy to forget just how radical he was in his own time. He's combative, brilliant, witty, and absolutely relentless. He picks fights with established authorities, writes in Italian instead of Latin so that ordinary educated people can read his work, and has a gift for designing experiments that cut through centuries of philosophical fog. Galileo's great contribution to our story, and it's one that often gets overshadowed by his telescope discoveries and his trial before the Inquisition, is his deep thinking about what it means to be in motion. He describes a thought experiment that's become one of the most important in the history of physics. Imagine, he says, that you're in the cabin of a large ship. The ship is moving at a constant speed in a straight line across perfectly smooth water. You have butterflies flying around the cabin. You have fish swimming in a bowl. You have a ball you can toss to a friend. Galileo argues, and he's right, that none of these activities will be any different whether the ship is moving or standing still. The butterflies don't cluster at the back of the cabin. The fish don't have to swim harder in one direction. When you toss the ball to your friend, you don't have to aim differently depending on which direction the ship is heading. Everything inside that cabin behaves exactly the same. This is what we now call Galilean relativity, and it's a genuinely profound idea. What it says, stripped down to its essence, is this: there is no experiment you can do inside a closed room that will tell you whether you're moving at a constant velocity or standing still. Constant, steady motion is indistinguishable from rest. Motion isn't some absolute thing that objects have or don't have. It's relative. You can only say you're moving relative to something else. Relative to the shore, the ship moves. Relative to the cabin, you're still. Both descriptions are equally valid. Neither is more true than the other. Think about what that means. It demolishes the Aristotelian idea that rest is a special natural state. Rest isn't special at all. Rest is just motion at zero velocity relative to whatever you've chosen as your reference point. And that choice is arbitrary. There's no cosmic signpost floating in space that says this spot is truly, absolutely still. Every motion is relative to something. Now Galileo also starts dismantling another Aristotelian idea, that objects naturally slow down and stop unless something keeps pushing them. Galileo does experiments with balls rolling down inclined planes, carefully timed, and he notices something crucial. A ball rolling down a slope speeds up. A ball rolling up a slope slows down. So what happens on a perfectly flat, frictionless surface? The ball should neither speed up nor slow down. It should just keep rolling forever. This is the seed of what Newton will later formalize as the first law of motion, the law of inertia. An object in motion stays in motion, at the same speed and in the same direction, unless something acts on it. The natural state of things isn't rest, it's constant motion, or rest. They're the same thing, really, just seen from different vantage points. Galileo publishes these ideas in his dialogue concerning the two chief world systems in 1632, and it gets him into enormous trouble with the church. The book is structured as a conversation between three characters, one defending the Copernican system, one defending the Ptolemaic system, and one supposedly neutral. But the defender of the old Earth-centered system is named Simplitio, and he's, well, simple. It's not subtle. The Inquisition hauls Galileo in, and by 1633, he's been forced to recant his support for the idea that the Earth moves, and he spends the rest of his life under house arrest. But the ideas are out there. You can't unring that bell. And here's what's beautiful about Galileo's relativity principle, even though it's centuries older than what we usually think of as relativity. It gives you the answer to that ancient question about why we can't feel the Earth moving. We can't feel it because we're moving with it. Everything around us, the air, the buildings, the ground beneath our feet, is all moving together at the same velocity. And uniform motion, motion at a constant speed in a straight line, is physically indistinguishable from rest. You only feel changes in motion, acceleration, deceleration, turning. The Earth's rotation does involve acceleration, technically, because moving in a circle means constantly changing direction. But the Earth is so large and turns so slowly that the acceleration is tiny, far too small for your body to notice in everyday life, There are subtle effects. Something called the Coriolis force influences weather patterns and ocean currents. But you, lying in bed, feel nothing. So Galileo has given us this beautiful framework. Motion is relative. There's no absolute rest. The laws of physics work the same whether you're moving steadily or standing still. And then, about 50 years after Galileo's death, along comes someone who takes these ideas and builds them into the most powerful scientific framework the world has ever seen. Isaac Newton, born on Christmas Day, 1642, in a small manor house in Lincolnshire, England, though whether it was really Christmas Day depends on which calendar you use, and that's a whole other story. Newton is, by almost any measure, one of the most extraordinary minds in human history. He's also difficult, secretive, vindictive, and capable of holding a grudge for decades. But what he does with the physics of motion is nothing short of revolutionary. He takes the scattered insights of Galileo, of Descartes, of Kepler, and he welds them together into a single, coherent system. 3 laws of motion and a law of universal gravitation. And with those 4 statements, he explains, well, nearly everything. The fall of an apple, the orbit of the moon, the tides, the trajectory of a cannonball, the shape of the earth itself. All of it, unified under one framework. It's breathtaking, really, when you think about what he accomplished. Let's start with those 3 laws, because they matter for our story. Newton's first law is, in a sense, Galileo's insight made official. An object at rest stays at rest, and an object in motion stays in motion at a constant speed in a straight line unless acted upon by a force. That's inertia formalized. Galileo had the intuition, but Newton makes it a law, the foundation stone of everything that follows. And notice what it's really saying. It's saying that uniform motion, steady speed, straight line, is the natural state. You don't need a force to keep something moving. You need a force to change its motion. That's the complete opposite of what Aristotle believed, remember? Aristotle thought you needed a constant push to keep anything going. Newton says no. You need a push to start, to stop, to speed up, to slow down, to turn. But cruising along at a steady clip, that takes care of itself. The second law gives you the details. Force equals mass times acceleration. If you push something, it accelerates. How much it accelerates depends on how hard you push and how massive the object is. Simple to state, incredibly powerful to use. This one equation lets you predict the motion of anything, as long as you know the forces acting on it. And the third law, for every action, there's an equal and opposite reaction. You push on a wall, the wall pushes back on you just as hard. A rocket expels gas downward, and the gas pushes the rocket upward. Forces always come in pairs. Now, Newton publishes all of this in 1687 in a book called the Principia Mathematica. And it's worth pausing for a moment on the circumstances, because they're kind of remarkable. Newton had actually worked out much of this years earlier, in 1665 and 1666, during the plague years, when Cambridge University shut down and he went home to that manor house in Lincolnshire. He was in his early 20s, and in the span of roughly 18 months, working essentially alone, he developed calculus, began his work on optics and the nature of light, and laid the groundwork for the laws of motion and gravitation. It's sometimes called the Annus Mirabilis, the miracle year, though it was really closer to 18 months. Either way, the sheer output is almost incomprehensible. But here's the thing about Newton. He didn't publish. He worked things out, wrote them down in his notebooks, and then just sat on them. For years, decades in some cases. He was intensely private and terrified of criticism. It took his friend Edmund Halley, yes, the comet guy, practically dragging the work out of him and personally financing the publication to get the Principia into the world. Without Halley, it's genuinely possible that Newton's masterwork would have stayed in a drawer. Think about that. The most important scientific book ever written, arguably, almost didn't happen because its author couldn't stand the thought of someone disagreeing with him. But it did get published, and it changed everything. And for our story, the story of relativity, what matters most is what Newton did with space and time. Because buried in the Principia, Newton makes a set of assumptions that are so fundamental, so deeply woven into the framework that most people don't even notice them. He assumes that space is absolute, and he assumes that time is absolute. And those assumptions will stand unchallenged for over 200 years. So what does absolute space mean? Newton imagined space as a kind of vast, fixed, invisible stage. It's just there. It doesn't move. It doesn't change. It doesn't depend on anything inside it. Objects move through space, but space itself is this immovable backdrop, stretching out infinitely in every direction. You can think of it like an enormous, invisible grid, always present, always still. And absolute time is similar. Time flows uniformly, everywhere, for everyone, at the same rate. A second is a second is a second, whether you're on Earth or on the moon or hurtling through the void at tremendous speed. Time is like a universal clock, ticking away in the background, and nothing you do, no motion, no force, no anything, can make it tick faster or slower. Now, here's what's subtle and important. Newton knew about Galilean relativity. He built it right into his laws. His first law essentially encodes it. If you're in a closed room moving at constant velocity, you can't tell you're moving. The laws of mechanics work the same in any inertial frame, meaning any frame of reference that's moving at constant velocity and not accelerating. Newton accepted all of that, but he still believed that behind all this relative motion, there was an absolute frame, a true state of rest, defined by absolute space itself. You might not be able to detect it through mechanical experiments, but it was there. It was real. It was, in Newton's mind, almost a theological necessity. He associated absolute space with the presence of God, the sensorium of God, he called it. Space was the arena in which God perceived and acted. This is a fascinating tension if you think about it. On one hand, Newton's own laws tell you that uniform motion is relative. You can't distinguish it from rest using physics. On the other hand, Newton insists that there is a true rest, a true motion, defined by absolute space. It's just that his laws of mechanics happen to be unable to reveal it. It's like having a law that says you can never find the treasure while simultaneously insisting, but the treasure definitely exists. It's not a contradiction exactly, but it's unsatisfying, and it will nag at people for centuries. But let's not get ahead of ourselves. For now, Newton's framework works spectacularly well. And I mean spectacularly. Over the next 2 centuries, Newtonian mechanics is applied to problem after problem, and it just keeps delivering. Astronomers use it to predict the motions of planets with extraordinary precision. Engineers use it to build bridges, design machines, calculate trajectories. When Halley uses Newton's laws to predict that a certain comet will return in 1758, and it does right on schedule 16 years after Halley's death, it's a triumph that cements Newton's framework as essentially gospel. When astronomers notice that Uranus isn't quite following its predicted orbit, they don't question Newton's laws. Instead, they say there must be an unseen planet out there, tugging on Uranus with its gravity. And in 1846, They point their telescopes at the spot where Newton's math says this invisible planet should be. And there it is. Neptune. Discovered not by looking through a telescope first, but by solving equations on a piece of paper. That's the power of Newtonian mechanics. It doesn't just describe the universe. It predicts things no one has ever seen. So for 200 years, absolute space and absolute time are just the water everyone swims in. Nobody seriously questions them. Why would you? The framework works. It works so well that by the late 1800s, some physicists are starting to wonder if there's anything fundamental left to discover. There's a famous, possibly apocryphal story about Lord Kelvin, one of the most prominent physicists of the Victorian era, saying something to the effect that physics is essentially complete, with just 2 small clouds on the horizon, 2 little puzzles left to clean up. And those 2 little clouds? They're going to blow the whole thing apart. But before we get to the storm, we need to talk about light. Because light is where the trouble starts. And the story of light is one of the great detective stories in all of science. People have been wondering about light for as long as people have been wondering about anything. Is it instantaneous? Does it take time to travel? The ancient Greeks debated this. Empedocles thought light must travel at some finite speed. Aristotle disagreed. He thought illumination was instantaneous, a change in the state of a medium rather than something moving through it. For centuries, Aristotle's view held sway, partly because light is so fast that no one could figure out how to measure it. Galileo actually tried. He and an assistant stood on hilltops about a mile apart with covered lanterns. The idea was that Galileo would uncover his lantern, and when his assistant saw the flash, he'd uncover his. Galileo would then time the round trip. It didn't work, of course. The speed of light is so enormous, about 186,000 miles per second, roughly 300,000 kilometers per second, that any delay over a distance of a mile is completely swamped by human reaction time. Galileo concluded that if light wasn't instantaneous, it was at least extraordinarily fast. The first real measurement came from an unexpected direction. In 1676, a Danish astronomer named Ole Romer was studying the moons of Jupiter, specifically Io, the innermost, large moon. He noticed something peculiar. The eclipses of Io, the moments when Io disappeared behind Jupiter, didn't happen at perfectly regular intervals. When Earth was moving toward Jupiter in its orbit, the eclipses came slightly earlier than predicted. When Earth was moving away from Jupiter, they came slightly later. Romer realized what was happening. When Earth is closer to Jupiter, the light carrying the news of the eclipse has less distance to travel. When Earth is farther away, it has more distance to travel. The variation in timing wasn't because Io's orbit was irregular. It was because light takes time to cross the extra distance. From the size of the discrepancy and the known dimensions of Earth's orbit, Romer estimated the speed of light. His number was off. He got something like 220,000 kilometers per second. But the important thing was that he proved light travels at a finite speed. It's fast, astonishingly fast, but it's not infinite. And this raises a question. A very deep question, actually, one that will eventually crack open the whole edifice of Newtonian physics, though nobody realizes it yet. If light is something that moves, something that travels from one place to another at a definite speed, then what is it, exactly? What's doing the moving? And what is it moving through? By the early 1800s, there are 2 competing theories. Newton himself had championed the idea that light is made of tiny particles. He called them corpuscles, little bullets of light shooting out from a candle flame or the sun. This made intuitive sense in some ways. Light travels in straight lines. It bounces off mirrors like a ball bouncing off a wall. The particle theory explained these behaviors neatly. But there was another camp, championed most forcefully by a Dutch physicist named Christian Huygens, who argued that light is a wave, like sound, like ripples on a pond. And in 1801, a young English polymath named Thomas Young performed an experiment that would tip the scales decisively. He shone light through two narrow slits and observed the pattern it made on a screen behind them. If light were made of particles, you'd expect to see two bright bands, one behind each slit. Instead, Young saw a pattern of alternating bright and dark fringes, an interference pattern. And interference is something only waves do. When the crests of two waves line up, they reinforce each other. You get a bright band. When a crest meets a trough, they cancel. You get darkness. Young's double-slit experiment was elegant, simple, and devastating to the particle theory. Light is a wave. But here's the thing about waves. Every wave anyone had ever encountered needed a medium to travel through. Sound waves travel through air. Ocean waves travel through water. Vibrations travel through a stretched string. So if light is a wave, what's it waving in? Out in the vacuum of space, between the sun and the earth, there's no air, no water, no obvious substance. And yet light clearly makes the journey. So there must be something out there, filling all of space, providing the medium for light waves to propagate through. Something invisible, intangible, and all-pervading. Scientists gave it a name. They called it the luminiferous ether, the light-bearing ether. And the search for this ether, the attempt to detect it, to measure it, to prove it exists, is going to lead physics into one of the most beautiful and consequential dead ends in the entire history of science. A dead end that would crack open our understanding of the universe itself. So let's talk about the ether. Because for a while there, it made perfect sense. It was the most reasonable hypothesis in the world. You've got light behaving as a wave, Young proved that, and waves need something to wave through. That's not a guess, that's just what waves are. A wave is a disturbance in a medium. Take away the medium and you don't have a wave anymore. You just have nothing. So the ether had to exist. It was a logical necessity, or at least it seemed like one. But think about what this ether would have to be like. It would have to fill all of space. Every gap between every star, every void between galaxies, every tiny pocket of vacuum inside your laboratory. It would have to be perfectly transparent, because we can see through it. It would have to be incredibly stiff, because light waves vibrate at tremendously high frequencies, and a medium has to be rigid to support high-frequency vibrations. That's just wave mechanics. And yet, it would also have to offer absolutely no resistance to the motion of physical objects, because the planets glide through space with no detectable drag. The Earth orbits the Sun year after year without slowing down, which means if there's an ether out there, the Earth is passing through it like a ghost through a wall. Already, you can feel the tension. You need something that's everywhere, incredibly rigid, and yet completely undetectable by any mechanical means. That's a tall order. But physicists in the 19th century were willing to accept those strange properties because the alternative, a wave with no medium, seemed even stranger. And besides, they figured, maybe we just haven't been clever enough to detect it yet. Maybe with the right experiment, we can catch the ether red-handed. And here's where the reasoning gets really elegant. If the ether fills all of space and is essentially stationary, a kind of universal reference frame, the thing Newton might have called absolute space made tangible, then the Earth is moving through it. The Earth orbits the Sun at about 30 kilometers per second. That's fast. That's roughly 100,000 kilometers per hour. So as the Earth plows through the ether, there should be an ether wind blowing past us, just like you feel wind on your face when you ride a bike on a still day. The air isn't moving, you are, but from your perspective, there's a breeze. Now, if there's an ether wind, it should affect the speed of light. Think of it this way. Imagine you're standing in a river and you shout to a friend upstream. Your voice, a sound wave traveling through the air, or in this case the water, has to fight against the current to reach them. It'll arrive a little slower than it would in still water. Now shout to a friend standing off to the side, perpendicular to the current. Your voice still has to travel through moving water, but the effect is different. It's subtler. The point is, the speed of the wave relative to you depends on which direction you send it compared to the flow of the medium. Same logic applies to light and the ether. If you send a beam of light in the direction the Earth is moving through the ether, it should travel a tiny bit slower relative to you. It's fighting the current. Send it perpendicular to the Earth's motion, and the effect should be different. The difference would be incredibly small, because light moves at about 300 million meters per second, and the Earth moves at only 30 kilometers per second. That's a ratio of about 1 to 10,000. So you're looking for a difference in the speed of light of roughly 1 part in 100 million. That's absurdly tiny. But by the 1880s, there was a man who believed he could measure it. His name was Albert Abraham Michelson, and he was, quite simply, the finest experimental measurer of the speed of light who had ever lived. Michelson was born in 1852 in what is now Poland, but his family emigrated to the United States when he was a child, settling in mining towns in California and Nevada during the gold rush era. His father was a merchant. Young Albert got an appointment to the United States Naval Academy, and it was there that he first became obsessed with optics and precision measurement. He was the kind of person who could look at an experimental setup and see where the errors were hiding. He had an almost artistic sensitivity to the behavior of light. By his late 20s, Michelson had already made the most precise measurement of the speed of light that anyone had ever achieved. He used rotating mirrors, a technique refined from earlier work by Léon Foucault, and got a value that was astonishingly close to what we use today. This was a man who understood light the way a jeweler understands gemstones, by feel, by instinct, by thousands of hours of careful looking. And Michelson realized something. You don't actually need to measure the absolute speed of light in 2 different directions and compare the numbers. That would require impossible precision. Instead, you can use interference. Remember Young's double-slit experiment? When 2 light waves overlap, they create interference patterns, bright and dark fringes, and those fringes are extraordinarily sensitive to tiny differences in the distance or time the 2 beams have traveled. Even a difference of a fraction of a wavelength of light, we're talking nanometers here, will shift the fringes visibly. So Michelson built a device that would split a single beam of light into 2 beams, send them off at right angles to each other, bounce them off mirrors, and bring them back together. If one beam had been slowed slightly by the ether wind and the other hadn't, or if they'd been affected differently, the interference fringes would shift. This device is called a Michelson interferometer, and it's one of the most important instruments ever built. Variations of it are still used today. In fact, the LIGO gravitational wave detectors that made headlines in 2015 are, at their core, giant Michelson interferometers with arms 4 kilometers long. But we'll come back to that. Michelson's first attempt was in 1881 in Berlin, in the basement of the Astrophysical Observatory in Potsdam, and it didn't quite work. The instrument was too sensitive to vibrations. Horse-drawn carriages rattling past on the street above were enough to blur the fringes. The results were inconclusive, but Michelson was not the kind of person who gave up. He teamed up with a chemist named Edward Morley, a meticulous experimenter in his own right at what's now Case Western Reserve University in Cleveland, Ohio. Together, they built a much larger, much more stable version of the interferometer. They mounted it on a massive sandstone slab, floating in a trough of liquid mercury, so it could be rotated smoothly without vibration. The whole apparatus was in the basement of a dormitory. They could rotate it to point in any direction, comparing the speed of light along the Earth's direction of travel through space versus perpendicular to it. In 1887, they ran the experiment, and the result was nothing, no fringe shift, or rather, a shift so small it was well within the margin of error, essentially zero. They rotated the apparatus. They tried different times of day, different times of year when the Earth's velocity through space would point in different directions. Nothing. The speed of light appeared to be exactly the same in every direction, regardless of how the Earth was moving. Let that sink in for a moment. This is genuinely strange. It's as if you're on that bike, riding at full speed, and you measure the wind and find there is none. Not just a little less wind than expected, no wind at all. As if the air doesn't exist, or as if somehow you aren't really moving. The Michelson-Morley experiment is often called the most famous failed experiment in the history of science, and that's a fair description, but it's also a bit misleading, because it didn't fail at all. It succeeded beautifully at measuring something. It just measured something nobody expected. It measured the absence of the ether wind. And that absence was a result that physics had absolutely no framework to explain. Now, physicists didn't immediately throw up their hands and abandon the ether. That's not how science works. When you get a result that contradicts your theory, your first instinct is to find a way to save the theory. Maybe the experiment was flawed. Maybe there's a loophole. And some very clever people proposed some very clever loopholes. The most important of these came from two physicists working independently: George Fitzgerald, an Irish physicist in Dublin, and Hendrik Lorentz, a Dutch physicist in Leiden. In the early 1890s, both of them proposed essentially the same idea. What if objects physically contract, get shorter, in the direction they're moving through the ether? If the arm of Michelson's interferometer that pointed along the Earth's motion actually shrank by just the right amount, it would exactly compensate for the slower speed of light in that direction, and the fringes wouldn't shift. The math worked out perfectly. The contraction needed was tiny, proportional to the square of the ratio of the object's speed to the speed of light. But it was precisely the amount needed to explain the null result. This is called the Lorentz-Fitzgerald contraction, and here's what's remarkable about it. It was proposed as an ad hoc fix, a patch, a way to save the ether. Fitzgerald and Lorentz weren't trying to revolutionize physics. They were trying to keep the existing framework intact, and the contraction they proposed seemed a little suspicious. It was exactly the right size to make the ether undetectable, which felt uncomfortably like a conspiracy of nature. But the math was solid, and it did explain the experiment. Lorentz, in particular, went further. Over the next decade, He developed a whole mathematical framework, what we now call the Lorentz transformations, that described how measurements of space and time would change for objects moving through the ether. He introduced a concept he called local time, a kind of mathematical fiction that made the equations work out. He didn't think local time was real exactly. He thought it was a useful trick, a bookkeeping device. The real time was still Newton's absolute time, ticking away uniformly everywhere. Local time was just what moving clocks happened to show, because of the way the ether affected them. And this is where things stand at the turn of the 20th century. The ether is still the reigning theory, but it's getting more and more complicated to defend. You've got length contraction, local time, an invisible medium with paradoxical properties, and an experiment that stubbornly refuses to detect any of it. The edifice of classical physics is still standing, but there are cracks in the foundation. And somewhere in Switzerland, a 26-year-old patent clerk with unruly hair and a habit of daydreaming about what it would be like to ride alongside a beam of light is about to look at all of this from a completely different angle. He's going to ask a question that seems almost childishly simple, and the answer is going to change everything, not just physics, the way you think about reality itself. His name, of course, was Albert Einstein, and by 1905, he'd been thinking about light for a very long time, since he was about 16, actually. That's when he first asked himself that strange, dreamy question. What would it be like to chase a beam of light, to run alongside it, matching its speed, and look over at it? What would you see? Think about that for a second. If light is a wave moving through the ether, and you could somehow travel at the speed of light right alongside it, you'd expect to see the wave just frozen, hanging there in space, motionless, like a snapshot of an ocean wave. A static electromagnetic field, oscillating nowhere, going nowhere. But here's the problem. Nothing in Maxwell's equations, those beautiful equations describing how electric and magnetic fields create and sustain each other, nothing in them allowed for a stationary electromagnetic wave. Maxwell's equations didn't care how fast you were moving. They always spat out the same answer. Electromagnetic waves travel at about 300,000 kilometers per second, period. There was no solution where the wave just sat there, frozen. So young Einstein had a contradiction on his hands. Galilean relativity said you should be able to catch up to anything if you moved fast enough. That's just how velocities add up. But Maxwell's equations seemed to be saying that light always moves at the same speed, no matter what. Both couldn't be true. And this bothered him. It bothered him for 10 years. Now, here's something important about Einstein in 1905. He wasn't a professor. He wasn't at a prestigious university. He'd graduated from the Swiss Federal Polytechnic in Zurich in 1900, but his academic career had stalled. He'd applied for academic positions and been turned down. He'd worked as a tutor, as a temporary teacher. Eventually, through a friend's father, he'd landed a job as a technical expert, third class, at the Swiss Patent Office in Bern. It was a decent job. He examined patent applications, mostly for electromagnetic devices, and it left him with enough mental energy to think about physics in his spare time, which he did voraciously, often in the evenings, often with his friend Michel Besso, an Italian-Swiss engineer who worked at the same patent office and served as Einstein's favorite sounding board. And this matters because Einstein's position as an outsider, not embedded in the academic establishment, not steeped in the daily assumptions of professional physicists, may have been exactly what allowed him to see things differently. The professors, the established physicists, they were all trying to fix the ether. They were trying to patch the existing framework. Einstein was free to throw it away. In June of 1905, he published a paper in the journal Annalen der Physik. The title was unassuming. On the electrodynamics of moving bodies. There was no dramatic preamble, no philosophical manifesto. Einstein just started with two postulates, two assumptions, and from those two assumptions, he derived everything. The first postulate was just Galilean relativity, upgraded. Einstein said, "The laws of physics are the same in all inertial frames of reference. Not just the laws of mechanics, which is what Galileo and Newton had established, but all the laws, including Maxwell's equations, including electromagnetism, including optics. There is no experiment you can do, mechanical, electrical, optical, anything, that will tell you whether you're in uniform motion or standing still. Full stop." The second postulate was the radical one. Einstein said, "The speed of light in a vacuum is the same for all observers, regardless of how fast they're moving or how fast the light source is moving. It's always the same value, about 300,000 kilometers per second. Always. For everyone." Now, you might hear that and think, well, that's a little weird, but is it really that revolutionary? And the answer is yes. Because those two postulates taken together are deeply incompatible with our everyday intuition about how speeds work. Think about it. If you're standing on a platform and a train goes by at 100 kilometers per hour, and someone on the train throws a ball forward at 50 kilometers per hour, you see the ball moving at 150 kilometers per hour. Speeds add up. That's Galilean velocity addition, and it's how the world seems to work. But Einstein is saying that if that person on the train turns on a flashlight instead of throwing a ball, you don't see the light moving at the speed of light plus 100 kilometers per hour. You see it moving at exactly the speed of light, the same speed the person on the train sees. The train's velocity doesn't add to it at all, and this isn't because of some weird property of the ether, or because your measuring instruments are being distorted, or because of some conspiracy of forces contracting your rulers. It's because that's just how the universe works. The speed of light is an absolute. So here's the obvious question. If the speed of light is the same for everyone, but different observers are moving at different velocities, something else has to give. If you can't change the speed, what changes? And Einstein's answer, the answer that shook physics to its core, was space and time themselves. This is where it gets really beautiful and really strange. Let's walk through one of the most famous thought experiments in the history of science. Einstein loved thought experiments. Gedanken experiment, he called them. And this one is sometimes called the light clock. Imagine you've got a clock that works by bouncing a pulse of light between two mirrors, one above the other, separated by some fixed distance. Every time the light pulse makes a round trip, up and back down, that's one tick. It's a perfectly good clock. Now imagine this clock is sitting on a train, and the train is moving past you at some significant fraction of the speed of light. From the perspective of someone on the train, the light just goes straight up and straight down. Simple. Short path. But from your perspective, standing on the platform, the train is moving sideways while the light is bouncing. So the light isn't going straight up and down. It's tracing a diagonal path, up and to the right, then down and to the right. A longer path. And here's the thing. The speed of light is the same for you as it is for the person on the train. Einstein's second postulate. The light doesn't speed up to compensate for the longer path. It travels the longer diagonal path at exactly the same speed, which means it takes longer to complete one tick. The moving clock ticks more slowly, Not because it's broken, not because the mechanism is affected by motion in some mechanical way, but because time itself, for the moving clock, is passing more slowly relative to you. This is time dilation. And it's not a metaphor. It's not an illusion. It's not a measurement error. It is a fundamental feature of the universe. And the math that falls out of this, the exact factor by which time slows down, turns out to be precisely the Lorentz factor. The same mathematical expression that Lorentz had derived years earlier as part of his ether theory. The same transformations, but where Lorentz had treated them as a mathematical convenience, a bookkeeping trick to account for the ether's effects on moving objects, Einstein showed that they were describing something real. There was no ether. There was no absolute time being secretly kept somewhere behind the scenes. The local time that Lorentz had dismissed as a fiction was the only time there was. It was real time. Your time depends on how you're moving. And it wasn't just time. Length contraction was real too. Not because the ether was squishing objects, as Fitzgerald and Lorentz had proposed, but because space itself contracts in the direction of motion. A meter stick moving past you at high speed is genuinely shorter than a meter stick at rest, not because any force is compressing it, but because the geometry of space-time makes it so. This is what made Einstein's contribution so profound. He didn't discover new math. The Lorentz transformations were already there. He didn't explain a new experiment. The Michelson-Morley result was already known. What he did was strip away the scaffolding. He got rid of the ether, got rid of absolute space, got rid of absolute time, and showed that you didn't need any of it. All you needed were two clean postulates, and everything else, time dilation, length contraction, the relativity of simultaneity, the invariance of the speed of light, all of it followed logically and inevitably. The relativity of simultaneity, by the way, is maybe the most mind-bending consequence of all, and it's worth sitting with for a moment. Two events that are simultaneous for one observer, say, two lightning bolts striking at the same instant, are not necessarily simultaneous for another observer moving relative to the first. It's not that one observer is wrong and the other is right. They're both right. Simultaneity is not absolute. It depends on your state of motion. There is no universal now stretching across the cosmos. No single present moment that everyone shares. Your now and my now, if we're moving relative to each other, are literally different slices through the fabric of space-time. And Einstein was 26 when he published this, working at a patent office, without access to a university library, talking things through with his friend Besso over coffee. The paper didn't even have any references, almost unheard of for a scientific publication. It was as if he'd built the whole thing from scratch in his head. But here's what's really remarkable about 1905. The special relativity paper wasn't even the only groundbreaking thing Einstein published that year. In the same volume of Annalen der Physik, he also published a paper explaining the photoelectric effect, the one that would eventually win him the Nobel Prize, in which he proposed that light comes in discrete packets of energy, what we now call photons. And another paper on Brownian motion, providing some of the strongest evidence that atoms actually exist. And then, almost as an afterthought, a short follow-up paper in September, where he derived perhaps the most famous equation in all of physics. He showed that mass and energy are equivalent, that they're two expressions of the same thing, E equals mc squared. The energy contained in a piece of matter is equal to its mass multiplied by the speed of light squared. And because the speed of light is such an enormous number and you're squaring it, Even a tiny amount of mass corresponds to a staggering amount of energy. A single kilogram of matter, if you could convert it entirely to energy, would release about 90 quadrillion joules. That's roughly the energy of a 20 megaton nuclear explosion. From 1 kilogram. This wasn't just theoretical elegance. This equation would eventually explain how stars shine by converting a tiny fraction of their hydrogen mass into energy through nuclear fusion. It would underpin the development of nuclear power and, more grimly, nuclear weapons. It connected the everyday world of matter to the ethereal world of energy in a way no one had imagined before. But in 1905, most of the physics community didn't immediately grasp the full significance of what Einstein had done. The papers were read, discussed, debated. Some physicists recognized their importance quickly. Max Planck, for instance, was an early champion, and his support helped bring Einstein's work to wider attention. Others were skeptical or simply didn't understand. Einstein remained at the patent office for several more years, not receiving his first academic appointment until 1908, when he became a lecturer at the University of Bern. And even then, his first lecture was attended by just 3 students, one of whom was his friend Besso. But the ideas were spreading, and Einstein himself knew that special relativity, for all its elegance, was incomplete. It had a limitation built right into its name. It was special. It applied only to the special case of uniform motion, of inertial frames, of observers moving at constant velocity in straight lines. It said nothing about acceleration. It said nothing about gravity. And gravity, as Newton had shown 2 centuries earlier, was the force that governed the cosmos. If Einstein's new framework couldn't handle gravity, it couldn't be the final word. So almost immediately after publishing Special Relativity, Einstein began thinking about how to extend it, how to build a theory that would work for all motion, accelerated, rotating, gravitational, anything. A general theory of relativity. And this is where the story takes a turn that even Einstein didn't expect, because the problem turned out to be far, far harder than special relativity. It would consume him for the next 10 years. It would push him to the absolute limits of his mathematical ability. It would involve wrong turns, dead ends, moments of despair, and a rivalry with one of the greatest mathematicians in the world that came down to a matter of days. Literally, days. The finish line of one of the greatest intellectual achievements in human history came down to a photo finish between 2 brilliant minds working feverishly in November of 1915. But we'll get there. First, let's talk about how Einstein even began to think about gravity in a new way, because the starting point is one of those deceptively simple observations that, once you really sit with it, changes everything. It's 1907, and Einstein is still at the patent office in Bern. He's been thinking about gravity, turning it over in his mind the way he always does, not with equations first, but with pictures, with thought experiments, with those little mental movies he runs in his head. And he has what he later called the happiest thought of my life. Now, that's a remarkable thing to say, right? Not the birth of his son, not his wedding, not even the moment he cracked special relativity. The happiest thought of his life was about falling off a building. Specifically, Einstein imagined a person falling freely from the roof of a house, and he realized something profound. While that person is falling, they wouldn't feel their own weight. If they let go of a ball, the ball wouldn't drop away from them. It would float right there beside them, falling at the same rate. Inside that little falling bubble, everything behaves as if gravity doesn't exist. You've seen this, actually. even if you haven't thought about it in these terms. Astronauts on the International Space Station float around, and we casually say they're in zero gravity. But they're not really. The station orbits at about 400 kilometers above Earth's surface, and at that altitude, gravity is still about 90% as strong as it is on the ground. The astronauts aren't escaping gravity. They're falling. They're in continuous free fall around the Earth, and because everything around them is falling at the same rate, they experience weightlessness. That's Einstein's insight from 1907, and he turned it into something he called the equivalence principle. Here's how it works. Imagine you're standing in a closed box, no windows, no way to see outside. You feel your feet pressing against the floor. You feel weight. Now, is that because the box is sitting on the surface of the Earth and gravity is pulling you down? Or is it because the box is out in deep space, far from any planet, but a rocket engine on the bottom is accelerating the box upward, pushing the floor into your feet? Einstein's claim was stunning. There is no experiment you can do inside that box to tell the difference. Gravity pulling you down and acceleration pushing you up feel exactly the same. They're not just similar. They are, in a deep physical sense, the same thing. And the reverse is true too. If you're in free fall, if the box is plummeting toward the Earth with nothing to slow it down, then inside the box, you can't tell the difference between that and simply floating in deep space with no gravity at all. Gravity and acceleration are two faces of the same coin. Now, you might be thinking, okay, that's a neat observation, but so what? And this is where Einstein's genius really shows, because he didn't just notice this equivalence. He took it seriously as a fundamental principle of nature and followed it wherever it led. And where it led was somewhere genuinely strange. Think about light for a moment. If you're in that accelerating box in deep space and a beam of light enters through a small hole on one side, what happens? Well, the box is accelerating upward, so by the time the light crosses from one wall to the other, the box has moved. From your perspective inside the box, the light beam doesn't travel in a straight line. It curves downward just a tiny bit. And here's where the equivalence principle bites. If acceleration bends light, and if gravity is truly equivalent to acceleration, then gravity must bend light too. A beam of light passing near a massive object like the sun shouldn't travel in a perfectly straight line. It should curve. That was a prediction, a testable prediction, and it was radical. In Newtonian physics, light has no mass, or at least the question was murky. So there was no obvious reason gravity should affect it. Einstein was saying something different. He was saying that gravity isn't really a force pulling on masses. It's something deeper, something geometric, something about the shape of space itself. But getting from that intuition to actual equations, that was the hard part, the brutally hard part. And it took Einstein from 1907 to 1915, 8 grueling years, to get there. Let me walk you through why it was so difficult, because the struggle itself tells you something important about how physics actually works, about how even the greatest minds can get stuck, go backward, and nearly lose the thread. The core problem was this. Einstein realized that if gravity bends light, then gravity must be affecting the geometry of space and time. Not just space, space-time, that four-dimensional fabric he'd already woven together in special relativity. Massive objects don't just sit in space-time and pull things toward them with some mysterious force. They warp the space-time around them. They curve it. And other objects, planets, moons, photons of light, everything, move through that curved spacetime along the straightest possible paths. What we experience as gravity, the pull that keeps your feet on the ground and the Earth orbiting the sun, is really just geometry, objects following the natural contours of curved spacetime. That's the big idea, and it's beautiful. But here's the thing. Einstein in 1907 didn't have the math. He knew what the answer should feel like. He had the physical intuition, but he didn't have the mathematical language to express it. The geometry of curved spaces was not something physicists typically studied. It was the domain of pure mathematicians, and it had been developed decades earlier by Bernhard Riemann, a German mathematician who in 1854 had laid out a general framework for describing spaces of any number of dimensions with any kind of curvature. Riemann had done this work in the abstract, as pure mathematics, with no thought of physics at all. He died young, at 39, of tuberculosis, never knowing that his mathematics would become the language of gravity. Einstein needed Riemannian geometry, and he didn't know it, so he had to learn it, and he turned to an old friend, Marcel Grossmann, the same classmate who had lent Einstein his lecture notes back at the ETH in Zurich, the same friend who had helped him get the patent office job. Grossmann was now a professor of mathematics, and Einstein essentially showed up at his door and said, "You have to help me. I need to understand this curved space mathematics." And Grossmann, to his enormous credit, dove in. He introduced Einstein to tensor calculus, to the Ricci tensor, to the whole apparatus of differential geometry. The two of them collaborated intensely, and by 1913 they published a joint paper, the Entwurf theory, from the German word for outline, that was a first attempt at a general relativistic theory of gravity. But it was wrong. Not completely wrong. It had many of the right features, and it got some predictions right. But the equations weren't quite correct. They didn't have the right symmetry properties. They didn't work in all coordinate systems the way Einstein felt they should, and Einstein knew something was off, but he couldn't figure out exactly what. He spent the next 2 years wrestling with these equations, trying variation after variation, sometimes convincing himself he'd found the answer, then discovering a flaw. There's a famous notebook, the Zurich notebook, where you can literally trace Einstein's thinking during this period. Pages and pages of calculations, false starts, crossed out equations, moments where he gets tantalizingly close to the right answer and then veers away because of a mistake or a misunderstanding. And this is where David Hilbert enters the story. Hilbert was one of the most brilliant mathematicians alive, based at the University of Göttingen, which was at that time arguably the mathematical center of the world. Einstein had been giving lectures about his work on general relativity, and in the summer of 1915, he gave a series of talks at Göttingen. Hilbert was in the audience, and he was fascinated. He saw the mathematical structure of the problem clearly, perhaps more clearly than Einstein did, because Hilbert was a far more powerful mathematician. And Hilbert decided to try to solve the problem himself. So now you have this extraordinary situation. Einstein, the physicist with the deep physical intuition but limited mathematical skill, racing against Hilbert, the mathematician with extraordinary technical power but less physical insight, both trying to write down the correct field equations of general relativity. They corresponded during this period, exchanging letters and ideas, and the relationship was collegial, but increasingly tense. Einstein was terrified that Hilbert would beat him to the finish line on his own theory, the theory he'd been building for a decade. November 1915 was the critical month. Einstein presented his work to the Prussian Academy of Sciences in a series of 4 Thursday lectures, each one refining and correcting his equations. On November 4th, he presented a version that was close but not quite right. On November 11th, another revision. On November 18th, he used his still incomplete equations to calculate something remarkable: the precession of Mercury's orbit, that tiny anomaly that had puzzled astronomers for decades, the 43 arcseconds per century that Newtonian gravity couldn't explain. And his equations gave exactly the right answer. Einstein later said that when he saw this result, he felt heart palpitations. He was so excited he couldn't work for days. He knew he was on the right track. And then, on November 25th, 1915, Einstein presented the final, correct field equations of general relativity to the Prussian Academy. The Einstein field equations. They're often written in a compact form that looks deceptively simple, a single line relating the curvature of spacetime on one side to the distribution of matter and energy on the other. But packed into that single line is an extraordinary amount of mathematical structure. 10 coupled, non-linear partial differential equations that describe how mass and energy warp the geometry of spacetime, and how that warped geometry tells matter how to move. Hilbert, meanwhile, had submitted a paper with essentially the same equations on November 20th, 5 days before Einstein's final lecture. For decades, there was a priority dispute. Who got there first? But when historians later examined Hilbert's original proofs, they found that the version submitted on November 20th was actually revised before publication, and the final correct equations appear to have been added after Hilbert saw Einstein's November 25th results. The consensus today is that Einstein deserves priority for the physics, for the conceptual framework, for the equivalence principle, and the physical reasoning that led to the theory. Hilbert deserves credit for independently deriving the equations through a different, more mathematically elegant route, using a variational principle that Einstein hadn't employed. And to Hilbert's credit, he always acknowledged Einstein's primacy, later saying, "Every boy in the streets of Göttingen understands more about four-dimensional geometry than Einstein." Yet, in spite of that, Einstein did the work, and not the mathematicians. So there it was. After 10 years of struggle, Einstein had his general theory of relativity. Gravity was not a force. It was geometry. Space-time was not a fixed stage on which physics played out. It was a dynamic, flexible, responsive fabric that curved and stretched and rippled in response to the matter and energy within it. The sun doesn't reach out and grab the Earth with some invisible rope. The sun's mass warps the space-time around it, creating a kind of curved valley, and the Earth rolls along the contours of that valley in what feels like an orbit, but is really just the straightest possible path through curved four-dimensional geometry. And this theory made predictions, not just the Mercury precession, which was a retrodiction, explaining something already observed. It made genuinely new predictions, things no one had seen yet, things that could confirm or refute the theory. The most dramatic of these was the bending of starlight by the sun, and the story of how that prediction was tested is one of the great adventure stories in the history of science, involving a world war, a solar eclipse, and a British astronomer who happened to be a Quaker pacifist in the middle of a war between his country and Einstein's. His name was Arthur Stanley Eddington, and he was, by 1915, one of the finest astronomers in England. He held the Plumian Chair of Astronomy at Cambridge, a position once occupied by some of the greatest minds in British science, and he was one of the very few people outside of continental Europe who actually understood Einstein's new theory. That matters more than you might think. During the First World War, Scientific communication between Britain and Germany had essentially collapsed. German journals weren't circulating in England. British scientists weren't reading German papers. There was a wall of hostility between the two scientific communities that mirrored the trenches in France. But Eddington had a connection. Willem de Sitter, a Dutch astronomer in neutral Holland, had received copies of Einstein's papers and forwarded them to Eddington in Cambridge. And Eddington read them. He didn't just read them. He grasped them deeply and became convinced that Einstein was right. This was not a popular position to hold in wartime England, championing the work of a German physicist while British soldiers were dying on the Western Front. And here's where Eddington's personal story intersects with the science in a way that's almost too perfect. As a Quaker, Eddington was a conscientious objector. He refused to fight. In 1918, as the war dragged on, he received a draft notice, and he was fully prepared to go to prison rather than serve in the military. His colleagues at Cambridge were horrified, not because they disagreed with his pacifism, necessarily, but because they didn't want to lose one of their best scientists. So the Astronomer Royal, Frank Watson Dyson, came up with a plan. Dyson had been looking at upcoming solar eclipses, searching for an opportunity to test Einstein's prediction about the bending of starlight. And he realized that the eclipse of May 29, 1919, was almost absurdly perfect for this purpose. On that date, the sun would be positioned right in front of the Hyades star cluster, one of the richest and brightest clusters visible from Earth. You'd have a whole field of bright stars right next to the sun's edge, exactly where the bending effect would be strongest. An opportunity like this wouldn't come again for years. So Dyson argued to the draft board that Eddington was essential, not for the war effort, but for a scientific expedition of national importance. The exemption was granted on the condition that Eddington would lead the eclipse expedition if the war ended in time. And the war did end in November 1918, just months before the eclipse. Now let's talk about what they were actually trying to measure, because this is where the physics matters. Einstein's general relativity predicted that starlight, passing close to the sun, would be deflected, bent, by the curvature of spacetime around the sun's mass. The predicted deflection was tiny, about 1.75 arcseconds for light just grazing the sun's edge. An arcsecond is 1/3600th of a degree. To give you a sense of how small that is, hold a coin, a penny say, and move it about 4 kilometers away from you. The angle that coin subtends at that distance is roughly 1 arcsecond. That's what they were trying to measure, the apparent position of a star shifting by less than 2 of those tiny units. And here's the thing that made this test so decisive. Newtonian gravity also predicted that light would bend around the sun, but only by half as much. If you treat a photon as a tiny particle with some effective mass and you apply Newton's law of gravitation, you get a deflection of about 0.87 arcseconds. Einstein's prediction was exactly double that. So this wasn't just a test of whether light bends near the sun. It was a test of whether it bends by the Newtonian amount or the Einsteinian amount. The factor of 2 was the whole game. 2 expeditions were organized. One, led by Eddington himself, went to the island of Principe, off the west coast of Africa in the Gulf of Guinea. The other, led by Andrew Crommelin and Charles Davidson, went to Sobral in northern Brazil. 2 sites, in case one had bad weather. And this was wise, because on the morning of May 29, 1919, Eddington woke up on Principe to rain. Heavy tropical rain. The kind of rain that makes you think the universe is personally opposed to your scientific ambitions. He later wrote about those anxious hours, watching the clouds, waiting, hoping. The eclipse was scheduled for the early afternoon. By midday, the rain had stopped, but the sky was still overcast. And then, as the moon began to slide across the face of the sun, the clouds started to thin. Not completely. The sky never fully cleared, but enough to get photographs. Eddington exposed plate after plate through his telescope, racing against the roughly 5 minutes of totality when the sun's corona was visible and the stars around it could be captured. He got 16 plates. Most were useless. The cloud cover had blurred the star images, but a few were workable. And when Eddington measured the positions of the stars on those plates and compared them to reference photographs of the same star field taken months earlier, when the sun was nowhere near it, the stars near the sun's edge had shifted. They had shifted by an amount consistent with Einstein's prediction, not Newton's. The Sobral expedition had better weather and clearer plates, and their results confirmed it. The deflection was approximately 1.75 arcseconds, right in line with general relativity. Now, I should be honest with you. The actual measurements were not as clean as the triumphant narrative suggests. The error bars were significant. Some of the Sobral plates from one of their telescopes actually gave results closer to the Newtonian value, and those were set aside because the telescope was thought to have been affected by the heat. Eddington has been criticized over the decades for cherry-picking his data, for being so convinced Einstein was right that he unconsciously biased his analysis. And there's probably some truth to that criticism. Modern reanalysis of the original plates suggests the results were genuine, but right at the edge of what the equipment could reliably measure. The experiment was repeated with better precision during later eclipses in 1922, 1929, and beyond, and each time the Einsteinian prediction was confirmed more convincingly. But in 1919, the result was real, if noisy. What was not noisy at all was the public reaction. On November 6, 1919, the results were formally announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room was packed. J.J. Thomson, the president of the Royal Society and the discoverer of the electron, presided. A portrait of Isaac Newton hung on the wall behind him, which everyone noticed and no one could ignore, because what was being announced was, in a sense, the overthrow of Newton's theory of gravity. Thomson called it one of the greatest achievements in the history of human thought. The next morning, the Times of London ran the headline, "Revolution in Science. New Theory of the Universe. Newtonian Ideas Overthrown." And within days, Einstein was the most famous scientist in the world, not just famous among physicists, famous the way movie stars are famous. His face was everywhere. He received thousands of letters. He was mobbed when he traveled. And this was strange because the theory that made him famous was one that almost no one actually understood. There's a famous, probably apocryphal story that a journalist asked Eddington if it was true that only 3 people in the world understood general relativity, and Eddington paused and said, "I'm trying to think who the third one is." But here's what's really interesting about the aftermath. General relativity was confirmed, celebrated, and then largely set aside for decades. Not rejected, just not very useful for most practical physics. The effects of general relativity are only significant in extreme conditions. Very strong gravitational fields, very high speeds, very large scales. For almost everything happening on Earth and in the solar system, Newtonian gravity works just fine. So general relativity became a beautiful, admired, somewhat lonely theory. Physicists called it a theorist's paradise, but an experimentalist's desert. There just weren't many ways to test it further with the technology available in the 1920s and 30s and 40s. Einstein himself spent the remaining decades of his life, he died in 1955, pursuing a unified field theory, trying to merge gravity and electromagnetism into a single framework. He never succeeded. And meanwhile, quantum mechanics was exploding into the most productive and practically useful theory in the history of physics, and Einstein found himself increasingly isolated from the mainstream, skeptical of quantum mechanics' probabilistic foundations, famously declaring that God does not play dice. The mainstream moved on without him, in a sense, but general relativity was not sleeping. It was waiting for technology to catch up, waiting for astronomers to discover objects extreme enough to make its predictions dramatically visible. And those objects were coming. In the 1930s, a young Indian physicist named Subrahmanyan Chandrasekhar, barely out of his teens, was on a steamship from India to England, and during that voyage, he worked out a calculation that would change our understanding of how stars die. A calculation that pointed toward one of the most extraordinary predictions of general relativity, something so strange that even Einstein himself refused to believe it could exist in nature. Chandrasekhar showed that there was a limit to how massive a white dwarf star could be, and beyond that limit, gravity would win, and the star would collapse under its own weight, with nothing in known physics strong enough to stop it. And that idea, that gravity could simply overwhelm everything else, was terrifying in its implications. Let's stay with Chandrasekhar for a moment, because his story is one of the most poignant in all of 20th century physics. He was born in 1910 in Lahore, in what was then British India. He was brilliant from the start, publishing his first scientific paper at 19. And it was on that steamship journey in 1930, traveling from Bombay to Southampton to begin graduate studies at Cambridge, that he made this remarkable calculation. He was 20 years old, sitting on a boat in the middle of the ocean, and he worked out that quantum mechanics, specifically something called electron degeneracy pressure, could only support a dead star up to a certain mass, about 1.4 times the mass of our sun, give or take. Below that limit, a star that has exhausted its nuclear fuel can settle into a stable white dwarf, held up by the quantum mechanical resistance of electrons being squeezed too close together. But above that limit, the electron pressure isn't enough. Gravity keeps winning. Now, here's the thing. Chandrasekhar arrived at Cambridge and presented this result, and the most famous astrophysicist in England at the time, Sir Arthur Eddington, the very same Eddington who had confirmed Einstein's light-bending prediction in 1919, publicly ridiculed him. At a meeting of the Royal Astronomical Society in 1935, Eddington essentially dismissed Chandrasekhar's work, arguing that nature would never allow such an absurd outcome as a star collapsing without limit. Eddington didn't have a rigorous counter-argument. He just found the conclusion aesthetically unacceptable. He said something to the effect that there ought to be a law of nature to prevent a star from behaving in this absurd way. And because Eddington was Eddington, a towering figure, the man who had made Einstein famous, his opinion carried enormous weight. Chandrasekhar was devastated. He eventually left England, moved to the University of Chicago, and built a magnificent career in astrophysics. He won the Nobel Prize in 1983, more than 50 years after that steamship calculation. But the damage Eddington did by dismissing that early work set the field back by decades. People simply didn't pursue the question of what happens when a massive star collapses, because the great Eddington had waved it away. And Einstein? Einstein agreed with Eddington on this particular point. In 1939, Einstein published a paper arguing that matter could not be compressed beyond a certain point, that the kind of complete gravitational collapse Chandrasekhar's work implied simply wouldn't happen in reality. The idea of what we now call a black hole, an object so dense that not even light can escape, was too strange for even the man who had rewritten the laws of space and time. But the mathematics didn't care what anyone found aesthetically acceptable. In 1939, the same year Einstein published his skeptical paper, J. Robert Oppenheimer, yes, the same Oppenheimer who would later lead the Manhattan Project, along with his student Hartland Snyder, published a paper showing that according to general relativity, a sufficiently massive star would indeed collapse through its own gravitational radius and form what they called a frozen star. They worked through Einstein's field equations and showed that from the perspective of a distant observer, the surface of the collapsing star would appear to slow down and freeze at the critical radius, the light from it redshifting into invisibility. But from the perspective of someone falling with the star, if you could somehow survive, you would pass right through that boundary in finite time and continue falling inward. The boundary itself, what we now call the event horizon, isn't a physical surface. It's a point of no return, a boundary in space-time beyond which the curvature is so extreme that all paths, even the path of light, lead inward. Think about what that means. In normal life, you can always turn around. You can always choose to go left instead of right, up instead of down. But inside an event horizon, the geometry of spacetime itself is so warped that outward ceases to be a direction you can travel. Every direction points toward the center. It's not that some force is pulling you in. It's that the structure of space and time has been bent so thoroughly that there is no path that leads out. That's what general relativity predicts, and it's extraordinary. But Oppenheimer and Snyder's paper landed just as World War II was beginning, and then Oppenheimer himself was consumed by the atomic bomb project, and the whole question of gravitational collapse was shelved for another 2 decades. General relativity went back to sleep. It woke up in the 1960s, and the alarm clock was a combination of new mathematics, new observations, and a new generation of physicists who weren't intimidated by the strangeness of what the equations were telling them. This period, roughly from 1960 to 1975, is sometimes called the golden age of general relativity, and it's when the theory finally came into its own as a living, testable, physically rich framework. The name black hole itself didn't even exist until 1967, when the American physicist John Archibald Wheeler coined it, or at least popularized it, at a conference. Before that, people used clunky terms like gravitationally completely collapsed object. Wheeler had a gift for language, and black hole was so vivid, so evocative, that it stuck immediately, and it changed how people thought about these objects. Suddenly, they had a name that captured the imagination. Around the same time, Roger Penrose, a brilliant British mathematician, proved something crucial. In 1965, Penrose showed that gravitational collapse to a singularity wasn't just a quirk of perfectly symmetrical idealized solutions to Einstein's equations. Earlier, skeptics had argued that real stars aren't perfectly spherical, and that any lumpiness or rotation would prevent complete collapse. Penrose proved them wrong. Using elegant topological arguments, he demonstrated that once an event horizon forms, a singularity, a point of infinite density where the known laws of physics break down, is inevitable, regardless of the shape or symmetry of the collapsing matter. This was a profound result. It meant black holes weren't mathematical curiosities. They were unavoidable consequences of general relativity whenever enough mass is concentrated in a small enough region. Penrose's collaborator on much of this work was a young physicist you've almost certainly heard of, Stephen Hawking. Together, Penrose and Hawking proved a series of singularity theorems in the late 1960s that showed singularities aren't just features of black holes. They're also a feature of the universe's own origin. Run the expansion of the universe backward, and general relativity predicts that you reach a singularity at the very beginning, a point where density and curvature become infinite. The Big Bang itself is, in a sense, a prediction of general relativity. And speaking of the expanding universe, let's circle back to that, because it's one of the most stunning predictions of general relativity, and Einstein himself initially refused to accept it. When Einstein first applied his field equations to the universe as a whole back in 1917, he found that they naturally predicted a universe that was either expanding or contracting. A static universe, one that just sits there, unchanging in size, was unstable in his equations, like a ball balanced on the tip of a pencil. But Einstein, like virtually every scientist of his era, believed the universe was static and eternal. So he added an extra term to his equations, a fudge factor called the cosmological constant, represented by the Greek letter lambda. This term acted as a kind of anti-gravity, a repulsive force that could balance the attractive pull of gravity and hold the universe still. Then, in 1929, Edwin Hubble, working at the Mount Wilson Observatory in California with its magnificent 100-inch telescope, discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe is expanding. It's not static at all. When Einstein learned of Hubble's observations, he reportedly called the cosmological constant the biggest blunder of his career. He had held the answer in his own equations and talked himself out of it because of a philosophical prejudice about how the universe ought to behave. But here's the kicker, and this is one of those twists that makes you love the history of science. In 1998, nearly 70 years after Hubble's discovery, two teams of astronomers studying distant supernovae discovered that the expansion of the universe is not just continuing, it's accelerating. Something is pushing the universe apart faster and faster. And the best mathematical description of that something? The cosmological constant, lambda. The very term Einstein added and then regretted. It turns out he may have been right for the wrong reasons. The cosmological constant, or something very much like it, what we now call dark energy, appears to be a real feature of the universe. It accounts for roughly 68% of the total energy content of the cosmos, and we still don't really understand what it is. General relativity predicted the framework, but filling in the physics behind dark energy remains one of the great open problems. So by the late 20th century, general relativity had gone from a beautiful but lonely theory to one of the most actively tested and observationally confirmed frameworks in all of science. Black holes, the expanding universe, gravitational lensing, where massive objects bend light from more distant sources, creating arcs and rings and multiple images, exactly as Einstein's equations predict. All confirmed. But there was one prediction that remained stubbornly undetected, one that Einstein himself had waffled on, first predicting them, then doubting their reality, then predicting them again. gravitational waves, ripples in the fabric of spacetime itself, propagating outward at the speed of light from violent cosmic events, colliding black holes, merging neutron stars, the most cataclysmic processes in the universe. Einstein's equations said they should exist, but they would be unimaginably faint by the time they reached Earth. The distortion they would cause in the space around us would be smaller than the width of a proton. To detect something that subtle, you would need an instrument of almost absurd precision, something capable of measuring a change in distance thousands of times smaller than the nucleus of an atom. And for decades, most physicists thought that was simply impossible. But not everyone. There was a man named Joseph Weber, a physicist at the University of Maryland, and in the 1960s he decided he was going to try anyway. Weber was an interesting character. He'd served in the Navy during World War II, survived the sinking of the aircraft carrier Lexington at the Battle of the Coral Sea, and later became an electrical engineer before turning to physics. He was tough, independent-minded, and not easily discouraged. And he built the first gravitational wave detectors, which were essentially large aluminum cylinders, about 2 meters long and 1 meter in diameter, suspended in vacuum chambers. The idea was simple in principle. If a gravitational wave passed through the cylinder, it would stretch and squeeze the metal ever so slightly, and sensitive piezoelectric sensors bonded to the surface could, in theory, pick up that tiny vibration. These were called resonant bar detectors because the cylinder was tuned to resonate at a particular frequency, around 1,660 Hertz, amplifying any signal at that frequency. And in 1969, Weber announced that he had detected gravitational waves. He said his bars were registering coincident signals, vibrations happening at the same time in detectors separated by 1,000 miles, which would rule out local noise. The physics community was electrified. If true, it would be one of the most important experimental results of the century. But here's the thing. Other groups around the world built their own resonant bars, tried to replicate Weber's results, and couldn't. Nobody else saw the signals he was seeing. The sensitivity of his instruments, when you worked through the numbers carefully, just wasn't good enough to detect the kinds of gravitational waves that astrophysical sources would produce. The signals he reported were far too strong, far too frequent, to be consistent with what general relativity predicted. By the mid-1970s, the consensus was that Weber had been mistaken, probably fooled by subtle instrumental artifacts or unconscious biases in his data analysis. He never accepted that verdict. He kept working on gravitational wave detection until his death in the year 2000, convinced he had seen something real. It's a poignant story. He was a pioneer who opened the field, who inspired an entire generation of experimentalists to think seriously about detecting gravitational waves, but who almost certainly never actually detected them himself. What Weber did accomplish, though, was something arguably more important than any single detection. He made the problem real. He showed that you could build instruments and go looking. And in the wake of his work, a new generation of physicists started thinking about how to build something vastly more sensitive. The key insight came from several people, but the names most associated with it are Rainer Weiss at MIT and Kip Thorne and Ronald Draver at Caltech, and the idea they pursued was fundamentally different from Weber's bars. Instead of waiting for a gravitational wave to make a chunk of metal vibrate, they would use light itself as the measuring tool. The concept is called a laser interferometer, and it's one of the most elegant measurement schemes ever devised. Picture this. You take a laser beam and split it into two beams traveling at right angles to each other, one going north, say, and one going east. Each beam travels down a long, straight tube, hits a mirror at the far end, and bounces back. When the two beams return to the point where they were split, they recombine, and because light is a wave, they interfere with each other. If both beams traveled exactly the same distance, they interfere in a very specific, predictable way. But if a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction. That means one beam's path gets slightly longer while the other gets slightly shorter. The round-trip distances change by different amounts, and when the beams recombine, the interference pattern shifts. You're essentially using the speed of light as a ruler to measure the stretching of space itself. Now, the amount of stretching we're talking about is almost comically small. For a gravitational wave from, say, two black holes merging 1 billion light-years away, the change in the length of each arm would be on the order of 10 to the -19 meters. That's a 10,000th the diameter of a proton. To have any hope of measuring that, you need the arms to be long, really long. So the tiny fractional change translates into as large an absolute change as possible. And you need the most stable, precise laser you can build, and mirrors that are as close to perfect as human technology can make, and isolation from every conceivable source of noise, seismic vibrations, thermal fluctuations, even the quantum uncertainty in the number of photons hitting the mirrors. Rainer Weiss worked out the basic noise budget for such a detector in a remarkable technical document in 1972, essentially listing every source of noise that would limit sensitivity and calculating what you'd need to overcome each one. It was a blueprint. And through the 1970s and 1980s, Weiss, Thorne, and Drever pushed to make it real, eventually convincing the National Science Foundation to fund what became LIGO, the Laser Interferometer Gravitational Wave Observatory. The scale of the project was staggering. Each LIGO detector, and they built two, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers so they could confirm real signals by checking for coincidence. Each detector has arms 4 kilometers long, 4 kilometers of ultra-high vacuum tube with mirrors so precisely polished that their surface irregularities are measured in fractions of a nanometer. The mirrors themselves, which they call test masses, weigh 40 kilograms each and are suspended on 4-stage pendulum systems to isolate them from ground vibration. The laser light bounces back and forth between the mirrors about 300 times before recombining, effectively increasing the arm length to about 1,200 kilometers. Building LIGO took decades. The initial proposal was in the 1980s. Construction began in 1994. The first version, initial LIGO, ran from 2002 to 2010 and detected nothing, which was actually expected because its sensitivity, while extraordinary by any normal standard, was still probably not quite good enough to see the kinds of events that happen frequently enough in the nearby universe. So they shut it down, spent 5 years upgrading every subsystem, better lasers, better mirrors, better seismic isolation, better everything. And in September 2015, advanced LIGO turned on. And here's where the story becomes almost too perfect. On September 14th, 2015, just 2 days before the official start of the first observing run, they were still in an engineering shakedown phase, just testing the instruments. Both detectors picked up a signal, a very specific signal, a chirp, a waveform that started low, rose in frequency and amplitude over about 0.2 of a second, and then abruptly stopped. The signal arrived at Livingston first, then at Hanford 7 milliseconds later, consistent with a gravitational wave traveling at the speed of light across the 3,000-kilometer separation between the two sites. When the team analyzed the waveform, matching it against the predictions of general relativity, the result was breathtaking. What they had detected was the final inspiral and merger of two black holes, each about 30 times the mass of the Sun, roughly 1.3 billion light-years away. In the last fraction of a second before they merged, those black holes were orbiting each other at nearly half the speed of light, and the gravitational wave power they radiated was, briefly, greater than the combined light output of every star in the observable universe. All of that energy, carried not by light, but by ripples in spacetime itself. And by the time those ripples reached Earth, after traveling for 1.3 billion years, the distortion they caused in LIGO's 4-kilometer arms was about 4/1000ths of a proton's diameter. And LIGO saw it. The detection was announced publicly on February 11, 2016, and it was one of those rare moments in science where you could feel the ground shift. This wasn't just confirming a prediction. It was the opening of an entirely new way of observing the universe. For all of human history, we had studied the cosmos using light, visible light, radio waves, X-rays, all forms of electromagnetic radiation. Now, for the first time, we could listen to the universe through gravity. It was like being able to hear after a lifetime of only seeing. Weiss, Thorne, and Barry Barish, who had taken over as director of LIGO in 1994 and transformed it from a struggling project into a functioning big science collaboration, shared the 2017 Nobel Prize in Physics. And the detections kept coming. More black hole mergers. And then, in August 2017, something even more remarkable, the merger of two neutron stars. This event, designated GW170817, was detected not only by LIGO and its European counterpart Virgo, but also by dozens of telescopes around the world and in space, because unlike black hole mergers, neutron-star mergers produce light, a kilonova, an explosion that forges heavy elements like gold and platinum in quantities you can barely fathom. For the first time, astronomers observed the same cosmic event in both gravitational waves and electromagnetic radiation. Multi-messenger astronomy, they called it. And it confirmed, among other things, that gravitational waves travel at the speed of light to an extraordinary degree of precision, within about 1 part in 10 to the 15th, exactly as Einstein predicted. So think about where we've traveled tonight. We started with Aristotle, with the simple human impulse to look at the world and ask why things move the way they do. We followed that thread through Galileo dropping, or maybe not dropping, objects from towers, through Newton sitting in his garden watching an apple fall and imagining a force that reaches across the void to hold the moon in its orbit. We watched the idea of light evolve from particles to waves and back again, and we followed the strange story of the aether, that invisible substance that everyone believed in and no one could find. We sat with Michelson and Morley in their Cleveland basement, staring at an interferometer that stubbornly refused to show what it was supposed to show. And then we met a young patent clerk in Bern who looked at all of that confusion and, instead of trying to fix the old framework, simply asked, what if the speed of light really is the same for everyone? What if that's not a problem to be solved, but a truth to be accepted? And from that one shift in perspective, everything followed. Time slowing down, space contracting, mass and energy being two faces of the same thing. And then the deeper revolution, the idea that gravity isn't a force at all, but the curvature of space-time caused by the presence of mass and energy. an idea so radical that it took Einstein himself nearly a decade of struggle, wrong turns, and desperate midnight calculations to work out the mathematics. An idea that predicted black holes before anyone believed they could exist, that predicted the expansion of the universe before anyone observed it, that predicted gravitational waves a full century before we built instruments delicate enough to feel them. What gets me, what I keep coming back to, is how human the whole story is. Every step forward came from someone who was willing to be confused, willing to sit with a problem that didn't make sense, and resist the urge to paper over the contradiction. Michelson expected to find the ether wind and didn't, and that null result, that apparent failure, turned out to be one of the most important measurements in the history of physics. Einstein's cosmological constant, the thing he called his greatest blunder, turned out to describe something real about the universe. Chandrasekhar was publicly humiliated for a calculation that was completely correct, and he had to wait decades for vindication. Weber was wrong about his detections, but right that the search was worth pursuing. Science doesn't move in straight lines. It loops and doubles back, and sometimes the most important discoveries look like mistakes at first. And here's the part that I find most comforting, especially late at night when the world feels complicated. General relativity tells us that space and time aren't fixed, aren't rigid, aren't the unchanging stage we once imagined. They flex and bend and ripple. The universe is dynamic all the way down to its geometry. And yet, within that dynamism, there are patterns, deep, beautiful, mathematical patterns that a handful of human beings managed to uncover using nothing more than thought experiments, pencil and paper, and eventually, extraordinary instruments. The same equations that describe the curvature of space-time around a black hole also describe the subtle bending of starlight that Eddington measured during an eclipse in 1919, and the faint chirp that LIGO recorded from 1 billion light-years away. One framework, spanning the smallest measurable distortions to the largest structures in the cosmos. We still don't have the complete picture, of course. General relativity and quantum mechanics, the two great pillars of 20th century physics, remain fundamentally incompatible at the deepest level. They work brilliantly in their own domains, but when you try to apply both at once, at the center of a black hole, or at the very first instant of the Big Bang, the mathematics breaks down. Somewhere, there's a deeper theory waiting to be found, one that will encompass both, the way general relativity encompassed Newtonian gravity. Maybe string theory, maybe loop quantum gravity, maybe something nobody has thought of yet. That's a story still being written, by people working right now, in offices and at chalkboards and on laptops, wrestling with the same kind of confusion that Einstein once wrestled with. And if history is any guide, the answer, when it comes, will probably be surprising. It will probably require letting go of some assumption we don't even realize we're making. But that's a problem for another night. For now, just let the story settle. Think about the fact that right now, as you lie here, gravitational waves are passing through you. Faint ripples from colliding stars and merging black holes scattered across the universe, stretching and compressing the space you occupy by amounts so tiny they might as well be nothing. And yet they're real. The universe is humming with them, a low, constant murmur of space-time flexing and relaxing, and we finally learned how to hear it. That's not a bad thought to drift off with. The universe is not silent. It never was. We just needed 100 years and a lot of very stubborn, very brilliant people to build the right kind of ear. So let that settle over you and rest easy knowing that even in the dark, even in the quiet, the cosmos is gently, ceaselessly rippling, and somewhere, someone is listening.